So let us start with limit, infinite limit. So infinite limit is the case when you as you approach to a number, x approaches to a number, the values of function grows as large as we want, well, either grows in a positive way or negative way. In other words, as we get closer to these kind of numbers, so let's say a here, the function values of the function grows like something like this, or let me just go from both sides, something like that, or it may go the other way around from negative side and so on. So this is where intuitive definition of the limit at plus infinity or negative infinity. Similarly, we can have negative infinity. What is important for us, the main source of generating infinity limit is when you have two functions and you're trying to find the quotient of those, limit of the quotients of two functions. And we know that the limit of the numerator as x goes to a is a number, not zero number, and limit of the denominator as x goes to a is a 0. Then in that case, we get either plus or minus infinity. There's one thing here that you have to note. Infinity limit is already does not exist limit. So you already know that this means that this limit does not exist. But plus minus infinity is a special case of does not exist. It says that, okay, out of all the craziness of does not exist, these guys are following very special case. When x approaches to a, they are either grow very big or small. And this is the main source. You may ask where this plus or minus come from. Well, basically, we look at the sign of this number and how gx approaches to 0. Does it approach from right or does it approach from left? And then, well, you have positive, positive, or positive, negative, and so on. You can find the sign. We will see in some examples for this case. Let me start just right away with some example. We have the quotient. As you remember, we always start with the limit of the denominator. And we see that this is a polynomial, and limit for polynomials is the same thing as evaluating those guys. And this will be 0. So limit in the denominator is 0. Limit in the numerator, it is 2 squared minus 3 times 2 plus 1. And that is 4 minus 6 plus 1, which is negative 1. Okay, so we have a number over 0. Well, you can say different things here. First of all, it is the limit does not exist. The second thing that you can say, it is infinite limit. You can go a little bit further and say that is this plus infinity or minus infinity? Okay, so that is something that now we are interested in answering. So in this case, the way we look at these kind of cases is that, okay, I will start with what we have, and we want to separate the function in the denominator, factor it in their pieces. Especially, we want to find where this x minus 2 is playing role. In this case, you see that x minus 2, x minus 5 are two factors. Okay, and then, well, look at the numerator. Numerator is always negative. Well, when we find the limit, it is negative numbers. So we are working around negative numbers. This piece here, as x goes to 2, this is also negative. It's approaching to negative 3. So it will be a negative number. How about this one? Oh, this. It really depends. Does we approach to 2 from left or right? Okay, so if we approach to 2 from the right, then this guy is going to be positive. Well, yeah, positive, that is what is this guy mean, and this is positive, yes. Now, positive, negative, and then another negative. All multiply, you get a plus infinity. Or the way I write this kind of cases is that -1 is in the numerator. In the denominator, we have negative here, positive here, but it will be close to 0. Sorry, negative, the numbers will be close to 0, but from the negative side. You see negative times positive. So then you have negative number in the denominator, negative number in numerator. It is going to be positive. But since we are dividing 1 by very small numbers, this is going to be plus infinity. Similar argument tells me that the limit of this function as x approaches to 2 from the left, this part is going to be negative, this part is going to be negative. So very small but positive numbers. In the numerator, we are going to have -1. So this will be negative. So this way, we were able to tell more and more specific information about this limit. Does not exist, was for all days. Now we know it is infinite limit. We know further, we know that when if you approach to 2 from the left, it is negative infinity, and when x approaches to 2 from the right, it is positive infinity. Any question, any comments here?
All good.
Okay. How about this one? Okay, so fractions always you start, oops. Another limit, regular, just quotient 1. So we always start
Teacher,
with.
sorry, teacher. Can you return the last page because I cannot wait to take the photos.
Sir, what was the question?
The last question.
Okay.
I think he wanted to take a screenshot, as I understand correctly. Am I right?
Yes. Yeah, can you return back the last page? Okay, thank you.
Okay, I won't go back.
No, teacher, I can.
Come on, Sinan, could you please turn off all the I don't know. Let me just do this thing. We discussed this thing last time that when if you have question, you have to ask when I am asking if there is any question. Otherwise, you post them on the chat bar. Okay. If you have question, you post them there. I will answer when it's the time. Um, okay, so now we have the quotient here again. I will start with the limit of the denominator. As x goes to 1, this is 1 cubed minus 2 times 1 squared plus 1, and that is 0. And the numerator, you see that, okay, this guy is going to give me, again, 1 squared minus 3 times 1 plus 2, which is 0. Okay. Now, this way, you notice that we have 0 over 0, and 0 over 0 is always, you have to deal with it. It is just beginning of the story, you have to try to find the vanishing factors. Here in the denominator, this is cubic. Cubics, we cannot factor easily, but in this case, there is an x common factor I can factor out, and that the rest is minus 2x plus 1. Numerator is quadratic. That's easy. Just x minus 1, x minus 2. Okay. And in the denominator, the quadratic part is x minus 1 squared. Now I have the vanishing factors. I cancel these two, and then this will give me limit of x minus 2 over x times x minus 1 as x goes to 1. And as you can see, well, this will give me, again, negative 1 over 0. Definitely, this limit does not exist. It's infinite limit, but is it positive or negative infinite limit? Okay, so here is where this whole analysis of left and right comes in. As x goes to 1 from the positive side, the numerator has a limit again. It has limit negative 1, but the denominator, this part is positive, this part is going to be positive. So very small but positive numbers. This will give me negative infinity. And for the right or left limit, this is negative 1 over 0. Small negative numbers, this will give us positive. Any question, any comments here?
No questions, but he still wants to see the previous question, if it's okay.
Do you have question for that?
No, I think he just wants to have a screenshot, right? I think it's enough time, hopefully.
Okay, so how about this question? Okay, so again, this is quotients of two functions. I will start with limit of the denominator, cosine of x as x goes to 0. Cosine is continuous function. So the limit and the valuation of the function at that point are the same. So this will give me 0. The denominator is 0. Secant of x as x goes to 0, it is limit of 1 over cosine x as x goes to 0. And this is 1 over cosine 0, which is 1 over 1. So 1 over 0, again, limit is either positive infinity or negative infinity. Now, we need to do something here to figure out that. One thing that always is useful, I'm hoping that you guys have noticed so far, that if you know graph of a function, you can use it in very nice way. For example, this is for cosine x. And as you know, cosine x is always less than 1. So cosine x is always less than equal to 1. Oh, okay. It is always bigger than equal to -1, but I don't care at this point because I get close to 1. When I get close to 1, as x gets close to 0, this cosine will be close to 1. But no matter what it's going to be, cosine of x minus 1 is going to be always a number less than or equal to 0. So if I want to make this one a little bit more precise, it will be, we have limit 1 in the numerator. In the denominator, our function approaches to 0 using very small negative numbers. So that tells me that the limit will be -infinity. Note that in this case, I didn't need to separate positive and negative side. So just goes ahead and you find that without any work there. Any question, any comments there?
Nope, all good.
Okay. Okay, how about vertical asymptotes? So the definition is just straightforward. A vertical line such as x equal to, remember the equation for vertical lines are x is equal to a number, is called a vertical asymptote for f if one of these happens. When x goes to a, the limit of the function is either plus infinity or minus infinity. And indeed, it is enough that this happens when x approaches to a from the left or x approaches to a from the right. So this is or this or that. So it's enough that one of these limits is either plus infinity or minus infinity. Then in that case, we call this vertical asymptote. And well, the way the graph would look like is, so let me just draw some x's here, some vertical lines. So for example, if x is approaching to a plus, that will give me positive infinity. That will be something like that, the graph of the function. When x approaches to a, we get limit of negative infinity. Well, the function can have very crazy work before this, but after a point, it will get close and close to this line, and so on. So basically, when we get closer to these guys from one side, the function's graph goes either up to infinity or down, grows as large as it can be, or negatively grows down as it can. Okay. You may ask, how do we find these things? So how to find vertical asymptotes? Well, the general, how do you do it in general is not easy, but for quotients or rational functions, and this is something that we can use actually in other cases. So when you have a polynomial over polynomial, so you have to first come up with the numbers a. What numbers you want to try to check the limit for. So first step is that find all x's which make the denominator 0. In other words, just solve qx equal to 0. Okay. Then you will get a list of numbers. The solutions are just candidates. The roots of the denominator are candidates for vertical asymptote. You say, why you say candidate? Because that's what second step will take care of. Because we may have a root of denominator such that when you find the limit is not positive infinity or negative infinity. The second step is that you check all these limits. So if you have 5 roots in the denominator, you check all these limits. See if it is an infinite limit or not. So check if this limit here is an infinite limit or not. So that's what we need to do. In general, this is the best way of work for the rational functions. Let me go for some examples here. Find all vertical asymptotes. So I will start with finding the roots of the denominator. X plus 1, x minus 1, x plus 2q equal to 0. This will give me right away either x plus 1 is 0, or x minus 1 is 0, or x plus 2q is 0. From this means that x is equal to negative 1, or x is equal to 1, or x is equal to negative. I have 3 candidates. So these are the candidates. And now I have to go ahead and find the limits of the function when x approaches to one of these numbers. So first, limit of f of x as x approaches to negative 1. Okay, so this is x times x minus 1, x plus 2 squared, x plus 1, x minus 1, x plus 2 cubed. As x goes to negative 1, you notice that in the numerator we will have 1, okay? So 1 times negative 1 minus, negative 1 times negative 1 minus 1, and negative 1 plus 2 squared. That number in the numerator is indeed what, 2? Yes. In the denominator, you will see 0. Well, it could be either plus or minus infinity, but for us, what matters is that this is infinite limit. And if you want to do it more carefully, when you go to plus negative 1 plus, this will be plus infinity, and for x approaching to negative 1 minus, this will be minus. And okay, so that's the first one. That right away tells me that, let me write it up here, x equal to negative 1 is a vertical asymptote of f. The second, limit of x goes to 1, x minus 1, x plus 2 squared over x plus 1, x minus 1, x plus 2 cubed. If you want to evaluate this limit, you'll notice that this is 0 over 0. And well, the factors you see here, you can cancel the vanishing factor and then find the limit, limit of x over x plus 2 squared over x plus 1 times x plus 2 to the power 3 as x goes to 1. And this will give 1 plus 2 squared, 1 plus 1, 1 plus 2. This is a number, obviously, yeah? So this will be 9 over what? 54, something like that. It is not positive infinity, and right away you can conclude that x equal to 1 is not a vertical asymptote. And for the last one, -2. Did we have? Yes, -2. So this will be x minus 1, x plus 2 squared, x plus 1, x minus 1, and x plus 2 to the power 3. This is again 0 over 0. Common, the vanishing factors are these two. You can cancel them. And what you find here is limit of x times x minus 1 over x plus 1 times x minus 1 as x approaches to -2 is what we have. Okay, I dropped the last term, which is x plus 2. There were 3 copies down there, 2 copies. So this way, what you get is, again, 2 times 2 minus 1, which is 2, over, this is -2. This will be different number. So this will be -2 times -3, 6. -1 times -3, 3. And then 0. Okay, so this will be either plus or minus infinity. Again, you can't fix exactly what is going on there, but right away from there, you can see that x equal to -2 is a vertical asymptote. Okay, so first find the roots of the denominator, check the limits. If the limit is infinity limit, then x equal to that number is a vertical asymptote for the function. Any question, any comments there?
Yeah, so one question is, are we canceling the factors one at a time specifically to test for vertical asymptotes that you can already predict may be asymptotes?
What was again question? The beginning I missed.
Are we just canceling the factors one at a time specifically to test for vertical asymptotes?
Okay, so there are 2 things. If, first of all, the question is written in a way that you say that from the beginning I can cancel. That's not right. You see, if you have a function like x times x minus 1 over x minus 1, this function, and when you cancel it, after that you get x. You may say, okay, I didn't do anything. I canceled just x minus 1. But these 2 functions are not the same. Not the same. Why? Obvious, because the domain of this function is everything but 1. But the domain of g is all throughout the R. So canceling the factors is not something that you can do without changing the function. That is possible when you're finding the limit. So yes, at the end we are canceling, but we are not changing function at the beginning. In the limit, we are allowed to do that. Okay? And the second thing is that this may seem easy to handle because it's already factored. But what if it is not factored? You have to do it yourself and then find everything. That's where all this complication shows itself better. Okay. Sinan, do you have any other question for me?
Yeah, sorry, I was answering as well. Let me check. Why is x equals 1 not a vertical asymptote than if it is cancelled?
A vertical asymptote has nothing to do with canceling or not canceling. The definition is straightforward. The limit as x approaches to that number must be infinity limit. We found a limit of a function as x approaches to 1 is a number, not infinity. It exists. It is 9/54. And that means that from that, we can conclude that x equal to 1 is not a vertical asymptote.
I actually answered your question, but still insist. So we have two vertical asymptotes, so we got to look more if we have 0/0.
I didn't get the question, Sinan.
So for this question, we do have two vertical asymptotes.
Yes, that's
if
correct.
It's 0/0, you need to check the limit if it gives you an infinity as you approach that point. Then you can say if it's a vertical asymptote or not.
Yes, yes. 0/0, I try always to mention this. 0/0 is not end of this story. It is just the beginning of this story. It just tells you, okay, you have to do something. 0/0 can lead to infinity. It can lead to a number. It can be, does not exist very badly, and so
on. Am I missing any questions, guys? Because a lot of people wrote stuff. I tried to ask some, answered the rest, but.
let me see for this one. Okay. Sinan, then is that okay? I move and then if
I think so.
Yeah.
I'll try to answer the rest in the chat.
Thank you. Okay. Another question. So here we have, okay, we have two functions added, this and that one. From the second one, when you look at that function, it is x/x minus 1. I will set the x minus 1 equal to 0 just to see what are candidates for this one. It is x equal to 1. And then, well, it's not done. I have to check limit of f of x as x approaches to 1 is limit of ln of x as x approaches to 1 plus x/x minus 1. Now, see, the limit of ln as x approaches to 1, ln is continuous function in its domain. As x approaches to 1, this is going to approach to ln of 1. But when x approaches to 1, x/x minus 1 approaches its infinite limit. So it means that it's either going to be big number or small number. Ln 1 is 0. So we are going to have infinite limit. Again, you can check more details. Limit. Well, for example, you can see that as x approaches to 1 from the positive side, the limit of the function is going to be plus infinity, and limit of x as x approaches to 1 negative is negative infinity. So from that, you can conclude that yes, x equal to 1 is a vertical asymptote. How about the other side? Well, this was just one candidate. Do we have any other candidate here? Well, Look at the graph of the function ln x, graph of ln x. This function, which is, by the way, the inverse of e to the power x, has a graph like that. It means that as x approaches to 0 from the right, limit of ln x is negative infinity. So that is the second point that we have to check. Means that we have to check what happens to f as x approaches to 0 from the right. This is ln of f of x, ln x, plus x over x minus 1 as x approaches to plus infinity. Oh, sorry, as x approaches to 0 from the right. And that, as you saw, will be negative infinity plus a 0. Okay, negative infinity, that is what we have. So that means that that's another vertical asymptote. So x equal to 1 is a vertical asymptote. And that's it for this one, because everywhere else ln is nice, x over x minus 1 is nice, their limit will be sums of the limits and never we get infinity limit. Are we good?
Yeah, I think so.
Okay. So now that we considered infinite limit, the next step is limit at infinity. Limit at infinity means that when we increase the value of x, so limit of f of x as x approaches to plus infinity is equal to L, if the values of the function get closer and closer to L, or as much as we want, we can make it close to L by increasing the value of x. In other words, the graph of the function when x approaches, so this is L, as the value of the x increases, it can be different forms, but it gets closer and closer to L. So I'll try to see if my closer and closer makes sense. And similarly, one can define the negative one. So limit of function as x approaches to negative infinity is L. If we have I can again draw the graph of the function as x approaches, as x gets negative and large negative numbers, the graph gets closer and closer to something, whatever the closer means. It could be like that. One important fact here is that the limit laws work for limit at infinity. So limit laws work for limit at infinity. It means that if you have two functions, the limits are a plus, or two numbers, you add them, the limit will be sums of their limits and so on. And another thing is that the other things I will go through the examples and explain some things in the examples as we go on. Sinan, should I stop maybe, or no? Are we okay?
Two questions popped up about the previous example.
Okay, do you want me to go back there?
Yes, please. So first one is x equals 0 not a vertical asymptote then?
Well, it is. It is. What? Sorry, you're right. Sorry, this is what I proved here is that x equal to 0 is a vertical asymptote because x was going to, yeah, thank you. So as x were getting closer to 0, yes, that is the vertical asymptote, x equal to 0.
All right, second is how did you find the second vertical asymptote? Could you go over it again?
Yes, so this is based on the fact that ln x has a vertical asymptote. That's based on the function ln x I knew. I know that ln x itself has vertical asymptote at 0. This is some of the things that you have to keep in mind based on the graph of the function. There are ways to show it, but this is what you need to keep in mind. I knew that x equal to 0 is a vertical asymptote for ln x, so I brought in as another candidate for vertical asymptote for this function, and along the way I showed that yes, even for this function, as x approaches to 0 from the right, we have an infinite limit. So it means that x equal to 0 is a vertical asymptote.
All right, is that clear? I think it's clear.
Okay,
No
good.
follow-up questions are coming. Yes, very good.
Okay, thanks. So one of the main things that you will notice at the infinite limit is that when you're applying the quotient rule, you may get infinity over infinity because you know the numbers are growing, and then so in these cases, well, we will probably go back to this later when we study the what's called L'Hopital rule. But for now, if you have a polynomial of polynomial and your function, you're trying to find the limit as x goes to infinity, you're going to get infinity over infinity. To resolve that indeterminate form, you factor, let me write it here, factor the x with the term with highest degree of x. So means what? Means that in the numerator and in the denominator, you look at the powers of x. Here is 2, this is 1. Here there is no x, that means that it's x to the power 0. Then factor out the highest power in the numerator, it is x squared. You may say, okay, wait a minute. How I'm going to factor out x squared if I don't have the factor in the other terms? Basically what you do, you divide all the terms by x squared. And you do the same thing with the denominator. In the denominator, the highest degree is 3. So I factor out x to the power 3 and x cubed over x cubed minus 2x squared over x squared plus x over x, x cubed, x cubed. I can simplify these terms. Why I'm going between different colors, I don't know. Limit as x approaches to plus infinity. See, first of all, I can cancel these two guys here. This is just x in the denominator. The second thing is that I can simplify the numerator. The numerator here will be, this part will be 1. The other one is 3 over x. And the other one is 2 over x squared. Here in the denominator, I have 1 minus 2 over x plus 1 over x cubed. Now, I am going to get, well, if I had that bracket from the beginning, I'm going to separate these two guys, hoping that these two guys are going to have limits, and using limit laws at infinity. So this will be limit of 1 over x as x approaches to plus infinity, and limit of 1 minus 3 over x plus 2 over x squared, 1 minus 2x plus 1 over x cubed as x goes to plus infinity. See, if I have x to the power a negative number, or 1 over x to the power positive number. So this is the fact I'm going to use. Let me just write it here somewhere. Limit of 1 over x to the power n as x approaches to either plus infinity or minus infinity is always 0, well, assuming that n is a positive. So just using that fact, I see that the limit of the first part is 0. The limit of the second part, using the limit laws, will be 1 minus 0 plus 0. 1 minus 0 plus 0. And this gives me 0 times 1, which is 0. So the limit of this function as x approaches to plus infinity is 0. One remark here, that if this was x approaches to negative infinity, it would go exactly the same way, and the limit will be 0 again. Okay, do we have question there?
No, but there is a small typo. So in the denominator, the last term is going to be 1 over x squared.
Oh, okay. Simplification of that one. Yes. You're right. Thank you. The result is the same thing, but you're right. Yes. Thanks. Okay, so then let's go to the next one. I am going to leave this one as an example for yourself to do it yourself. And the limit here, well, maybe I quickly go over, but I will let you do the whole work there. So the limit of x goes to negative infinity, I factor out the highest power, x to the power 5, x to the power 5 in the numerator, 3 minus 1 over x plus 2 over x cubed minus 1 over x to the power 5. Here in the denominator, 1 plus 1 over x cubed plus 3 over x to the power 5. And then you cancel these two. You will get the limit of just the simple case. Why I'm saying it is simple? Because just by knowing the fact that limit of 1 over x to the power n as x approaches to plus or minus infinity, if n is a number bigger than 0, this is going to be 0. Just by knowing that, and knowing that the limit laws work for limit at infinity. So that way you can separate these guys, quotient and then sum, constant, multiple, you use all of those, and you get 3 minus 0 plus 0 minus 0, 1 plus 0 plus 0. And that will give you 3. Are we okay now?
All good.
Okay. This is the one I will give you as an example for you to do it. So if you want to screenshot this one, please go ahead. This is straightforward. Again, the key point is factor out the highest powers of x from the numerator and denominator and do the simplification. Okay. Okay, how about this one? Okay, so first thing first is that this is not a polynomial over polynomial. But what you should notice here is that in the numerator, we have square root of a polynomial. So again, we can do the same story here. So need to factor out the x, the term with highest power of x. So in other words, here we have, so in the numerator, I can factor out x squared from the numerator under the root. So it will give me x squared over x squared plus 3x over x squared minus 1 over x squared. In the denominator, highest power is x, so it will be x over x plus 1 over x. Very nice. Now, just by looking at this piece here, I see that, okay, product of two factors, then square root. This is the same thing as root A, root B, if both of them are positive, okay? Now, that means that the numerator, we can write it as root x squared, root the rest, yes? So the rest, let me just write that one, root x squared and root 1 plus 3 over x minus 1 over x squared, x 1 plus 1 over x. And x goes to negative infinity. Here, that important fact, root of x squared is not x. It is absolute value of x. So this guy here, sitting there, is not x. It is absolute value of x. But since x is going to negative infinity, so it will be just negative numbers. For negative numbers, absolute value of x is you need to multiply another negative sign to x to make it positive. So that means that that absolute value up there is going to be negative x root 1 plus 3 over x minus 1 over x squared over x times 1 over 1 plus 1 over x. Now that we are done with the absolute value, with this root, all those things, I can cancel these two, and I have one limit. And applying the fact that we have been using and the limit laws for limit at infinity, we will get root 1 plus 0 minus 0, 1 plus 0. And this is root, oh, there was a minus sign. I forgot that minus 1 over 1. And that is, and this is how we find the limit as x goes to negative. The idea is the same thing. So try to factor out the highest power, but you may need to do a little bit of more work. Any question, any comments there, Sina?
No questions. I think we resolved everything, but in the previous question, if you could tell us the answer, because some students privately messaged.
Oh, this is going to be 0.
Yes.
Yeah.
And someone asked about the next question, how did we get the negative?
Oh, okay. So up to here, I'm assuming that it should be okay up to here. The key point is this fact, root of x squared is absolute value of x. Never write root of x squared is equal to x. That's a huge mistake. But we are trying to let x go to negative infinity. It means that we are working with negative numbers. Absolute value of a negative number, so for example, absolute value of -1 is 1. In other words, for negative numbers, we have to multiply another negative sign to that number to make it positive. That's why this absolute value here turned into the whole negative x there.
And Haley asks, why is the root x squared is absolute value x? It's root of x squared. Haley.
Oh, the question is what?
Question is, why is root x squared is equal to absolute x?
Why? So what is the alternative there? So you may say that I put x, yes? So let me give you an example. Root of -1 squared is what? Is root of 1. And root 1 is just 1. It's not -1. So this is showing that root x squared is not equal to x. It is equal to absolute value of x. So keep this in mind. Well, there are good reasons for that. For example, x squared and root are not inverse of each other. That's the reason that this root x squared is not equal to x. By the way, x squared is not 1 to 1, so it should not have any inverse. Okay, so that means that why we have this problem here.
I think we're good. That's all.
We're good? Okay. Okay, so how about this one? Tan inverse and 2 to the power x. So there are, other than those 1 over x, so far, remember that we have done limit of 1 over x to the power n as x goes to plus infinity or minus infinity. This is 0 if n is a negative number, a positive number. There are a few more things that you have to know, and that is related to the exponential function. For exponential function, b to the power x, as x goes to plus infinity, it is plus infinity if b is a number bigger than 0. And if we are trying to find limit of b to the power x as x goes to negative infinity, this is going to be 0 if, yes, for b bigger than 1. In other words, the graph of exponential function for a base bigger than 1 is like that. B to the power x for b bigger than 1. So these two I should put in the box. The second one is that, okay, so the same things are for limit of b to the power x if b is a number, base is a number between 0 and 1. But this time, as x goes to plus infinity, this is 0, and this other guy is plus infinity. Actually, one can conclude that using the previous fact, but here I'm going to assume that you know that based on the graph of b to the power x for base less than 1 and bigger than 0. Okay, one more thing. It is that limit of tan inverse x as x goes to plus infinity and limit of tan inverse x as x goes to negative minus infinity These two are two numbers that you should know. How I know that? Remember the graph of tan inverse, which by the way, you can find by reflecting the graph of tan x with respect to line y equal to x. That guy is something like this. So this is as x goes to plus infinity, you get to pi over 2. As x goes to negative infinity, this goes to negative pi over 2. So these are basically three things that you have to know to start with when you're working with limit at infinity. But what does that will bring for us? So let me just push everything down there. So here, limit of 2 to the power x plus tan inverse x as x goes to plus infinity. Well, I'm hoping that I will be able to find limit of both sides and use the limit laws. As x goes to infinity, 2 to the power x, you multiply 2 to itself as big as you can. This is going to be plus infinity, and limit of tan inverse as x goes to plus infinity is pi over 2. So you're going to have large number. Here I'm showing it by plus infinity, and a number which grows large and large. So it's not just a number, it is a trend, it is growing. Plus just a constant, it will still grow up to plus. Just as an extra fact, so if the limit was as x goes to negative infinity, 2 to the power x plus tan inverse of x, here you will have limit of 2 to the power x as x goes to negative infinity plus limit of tan inverse x as x goes to plus. Here, the limit of 2 to the power x to the power negative infinity. Look at the graph. B is 2, it is bigger than 1. As x goes to negative infinity, it approaches to 0. So the first part is 0. The second part is, oh, this must be negative infinity. As x approaches to negative infinity, tan inverse approaches to minus pi over 2. So the whole limit here will be negative pi over 2. So that way, you find the limits of this form. Sinan, do we have any question, any comments?
So far, nobody asked anything. So we're good.
Okay. Okay, how about horizontal asymptotes? So this is definition. A horizontal line remember, horizontal lines are given by equation like y equal to a number is a horizontal asymptote of f if when you finding limit of the function at infinity, you get that number b, or when you get the limit of that function as x goes to negative infinity, you get b. Either of these guys, you get a number, y equal to that number is horizontal asymptote. Okay, I need to add 2 remarks here. Remark 1 is that Well, when you're trying to find the limit as x goes to plus infinity or minus infinity, you can at most get two different numbers, one for plus infinity, one for negative infinity. So a function can have at most two horizontal asymptotes. There is no function with three horizontal asymptotes. Functions can have either non-horizontal asymptote, zero horizontal asymptote, or two horizontal asymptote. The second thing is that unlike the vertical asymptote, you don't need to be worried about what we are going to let x go to infinity. You don't need to find that candidates. You just start finding limits. So to find horizontal asymptotes, we just find these two limits. We check two limits. If they are number, if the limits exist, in other words, are number, y equal to those numbers is or are horizontal asymptote. Just go ahead and find two limits. That's it. It's not like the vertical asymptote. In the vertical asymptote, you have to find the candidates for x and then find limit as x goes to a, and then you may have infinitely many vertical asymptotes. Look at the tangent function. It has infinitely many asymptotes, vertical asymptotes. Here, you just find two limits. It's easy if the limit at infinity, positive infinity or negative infinity is a number, y equal to that number is the horizontal asymptote. Okay, let's see these ones in examples. Okay, for example, this one. This is basically a little bit more advanced version of what we did before. Remember, okay, so let me start with this. The question asks what are the horizontal asymptotes of this function. Means that we have to check two things. Limit of function as x goes to plus infinity and limit of the function as x goes to negative infinity. And see which one gives you a number. Well, when we do the first one, you notice that we have worked with these guys before. Yes, we did. Actually, if you go back to those three examples back, you saw that I will factor out the highest powers of x. So in the numerator, I will have root x squared, root of 1 plus 3 over x minus 1 over x squared plus x. And in the numerator, 1 plus 1 over. We are not done because we haven't factored out the whole thing. But here is where, again, that absolute value of x shows itself. Root of x squared is absolute value of x. But since we are going to positive infinity, so as x approaches to plus infinity, so we are dealing with positive numbers, then absolute value of x, you can replace it by just x. That means that in the numerator, we are going to have x root 1 plus 3 over x minus 1 over x squared plus x over x 1 plus 1 over x as x goes to plus infinity. Now, You see there is an x here and x here. I can factor that x out. So limit of x root 1 plus 3 over x minus 1 over x squared plus 1. And there's x1 times 1 plus 1 over x there. And x goes to plus. This cancels with that, and then apply the limit laws. You will get 1 plus 0 minus 0 plus 1, 1 plus 0 in the denominator. So this will be 2 over 1, which is 2. So we found a limit of f of x as x approaches to positive infinity, and we found that is a number. So right away you can go ahead from there and say that y equal to 2 is a horizontal asymptote for f. Okay, so this is one of these limits gave us one horizontal asymptote. Now we have to check the other limit. Let's see what will happen for the other limit. Well, the computations actually will go very similar to the previous one. So let me just copy this piece. And then paste it here. Okay, but always we are working with x approaching to negative infinity. As x approaches to negative infinity, absolute value of x is negative x. So what we are dealing with here is limit of x negative infinity minus x 1 plus 3 over x minus 1 over x squared plus x. And then the rest is again similar to what we had before. I can factor out x. This time there will be that extra negative sign. As x goes to negative. And then, well, this cancels with that. Then apply the limit laws for a limit at infinity. You get negative root 1 plus 0 minus 0 plus 1, 1 plus 0. So this will negative root 1 plus 1 over 1, which is equal to 0 over 1, and that is 0. In this example, both of limit at positive infinity and negative infinity, both of them exist. They are numbers, and each one, they are different numbers. So we will have, right away from here, y equal to 0 is another horizontal asymptote for f. So this example has exactly the maximum number of horizontal asymptotes that we can have. Any question, any comments?
I think we're good.
Very good, thank you. Okay, let's do another example. Oh, okay, this example is a little bit different example in nature. When we are dealing with horizontal asymptotes, always, you start with just writing the limits of these two functions, this function as x goes to plus infinity or minus infinity. When I found limit of 2x minus 3x over e to the power x plus 5 to the power x, all of them are going to be infinity. Actually, it will be negative infinity over infinity. So this is going to be something that we have to deal with carefully. Remember, when we had polynomial, we factor out the x with the highest power. When x goes to plus infinity, we will do the same thing with the exponential function. So factor out the exponentials with the highest base. Oops. It's like x going to infinity case, so the polynomials means what? In the numerator, you look, okay, there's base 2 and 3. The highest will be 3 to the power x. And then factor out will be 2 to the power x, 3 to the power x, minus 3 to the power x over 3 to the power x. And in the numerator, E is 2.71 and 5 is, well, obviously bigger than that. So I need to factor out 5. As x goes to plus. Now, I will separate these two. And using the fact that if you have a over b to the power x, this will be same thing as a over b to the power x. Okay, so that's a fact that I'm using here. Now I can rewrite this thing as 3 over 5 to the power x as x goes to plus infinity, hoping that I will be able to find the limit of these guys. So this will be 2 over 3 to the power x minus 1. This will be e over 5 to the power x as x goes to plus infinity plus 1. Now, the reason that we are factoring out the highest base is all here. This is where it plays a very important role. You see, 2 over 3 is a base less than 1. And the same is for this guy. And we know that limit of b to the power x, if b is less than 1, as x goes to plus infinity, this is going to be 0. So as a result, the first part is going to be 0. The second part is going to be 0 minus 1 over 0 plus 1. And that is 0 times negative 1. And 0 times negative 1 is just 0. Limit of the function as x approaches to plus infinity is a number. So I can go ahead and conclude that y equal to 0 is a horizontal asymptote. So that is halfway through. So we found as x approaches to plus infinity what is happening to this function, and we proved that that's a number. How about when x goes to negative infinity? Well, if you do the calculation here, you see b to the power x as, let me go back to this. Limit of 2 to the power x minus 3 to the power x over e to the power x plus 5 to the power x as x goes to negative infinity. 2 to the power x, base is bigger than 1, and x goes to negative 0. So this will be 0 minus 0 over 0 plus 0. So this is something 0 over 0. We have to resolve that. How do we resolve this kind of 0 over 0? Listen, this is new thing. We, as x goes to negative infinity, we know that if b is less than, b is bigger than 1, b to the power x is going to be, to have limit 0. That's why for x going to negative infinity, we will factor out exponents with lowest base. So this means that I can factor out 2 to the power x. So this will give me 1 minus 3 over 2 to the power x. And here will be e to the power x. This will be 1 plus 5 over e to the power x as x goes to negative. And now we separate this. This will be 2 over e to the power x, limit of 1 plus 3 over 2x, 1 plus 5 over e to the power x, as x goes to negative. So look at the base. So when you have exponential function, look at the base. Is it bigger than 1 or less than 1? In this case, it is less than 1. Okay, so the limit of b to the power x when base is less than 1, as x goes to negative infinity, this is going to be positive infinity. And limit of these guys, 1 plus, 1 minus, this should be minus. 3 over 2 is a number bigger than 1. To the power negative infinity, that is 0. 1 plus e, 5 over e is a number bigger than 1. To the power negative infinity, that's another 0. So that means that we have plus infinity times 1. So you're going to have large number, and you multiply it by 1, you still get large number. For this part, we didn't get a number. So it means what? It means that we don't have any other horizontal asymptote. This is the only horizontal asymptote of this one. Just check 2 limits. Which one gives you a number? That will give you a horizontal asymptote. In this case, only one of them gave us a horizontal asymptote, and this is y equal to 0. Any question, any comments here?
Yeah, so the question is, do we factor out the exponent with the lowest base when limit x goes to negative infinity
Yes.
is equal to 0 over 0?
Yes. Any other?
That was it.
Okay. So that's it. So those are the examples we wanted to do for the horizontal. Now we are going to talk about the differentiability. So the definition goes like this. F is differentiable at x equal to a if the limit is given by this f of x minus f of a over x minus a as x goes to a, or an equivalent version of that, limit of f of x plus, so I will put this one in a bracket, but these are the same thing, so equivalent. F of x plus h, f of a plus h minus f of a over h as h goes to 0. Either that limit or the other one, doesn't matter. Those are going to give you the same thing. The limit exists. So that is the definition. That is when we say that function is differentiable at that point. And then we go ahead and we write the value of the function, and we write the value of that limit. We write it as f prime at a. So value of the limit. Maybe one question that can come up here is that why are these two equivalent limits? Actually, you can go from this guy to this limit by changing variables. Set new variable h to be x minus a. From that, you can conclude that a plus h is indeed equal to x. That's why you see for x, we are plugging in a plus h. And you see that since x is approaching to a, then x minus a will approach to 0. And that's why instead of x going to a, you see that we have h going to 0. Either will work. Any of these ones you put, it will work. You have to be only careful that when you're using one, you don't confuse with any other components from the other one. This is just a definition, and let's just go through some examples, maybe something over there if you have any question. Sinan, is there anything that I need to answer at this point?
All good.
Okay, perfect. Well, let's just do some questions here. So check if this function is find the derivative of this function by the definition of the derivative. Well, right now you know all these differentiation rules. You can go ahead and just differentiate this guy. This is equal to 2x minus 2. I know that. I am not interested in the derivative. I want you to see that you can use the definition of the derivative and find the derivative of this guy. Let's say at any point A. Okay, so for me, I will start with, well, the version that f of a plus h minus f of a over h as h goes to 0. If this exists, I'm going to denote this by f prime at a. What is this guy? So I evaluate f at a plus h. So it will be a plus h squared minus 2 times a plus h plus 4. That's just first part, minus f of a. So a squared minus 2a plus 4 over h as h goes to 0. This guy. Now, expand it. The first one will be a squared plus 2ah plus h squared minus 2a minus 2h plus 4 minus, I multiply minuses inside, a squared plus 2a minus 4 over h. Right away, you notice that, okay, this negative 4 cancels with plus 4. 2a cancels by negative 2a. A squared by a squared. So my limit is basically limit of 2ah plus h squared minus 2h over h as h goes to 0. Well, polynomial of polynomial, evaluate, you get 0 over 0. So I have to factor out the vanishing factor. Vanishing factor is h minus 0, which is h. So I factor that 2a plus h minus 2 as over h as h goes to 0. Cancel the vanishing factors. You find the new limit. As h goes to 0. And this is equal to 2a plus 0 minus 2, which is 2a minus 2. And that is what you get from the differentiation rules as well. Any question, any comments here?
All good.
Okay. So then we can go to the next example. So this is where it shows itself. if we are interested in finding the derivative of function as at x equal to 0, we cannot use differentiation rules, because differentiation rules only work for the functions which are defined by one formula, a good formula that we know how to differentiate each component of that, and then you differentiate the whole thing, yes? But here, this is piecewise defined function, and x equal to 0 is actually a point which is not very nice. It is where the function is going to have two different formulas at x equal to 0, at anything which is not equal to 0. Well, here, what I'm trying to say is that you don't have any other method but using the definition of the derivative. So here means that we need to find either of those two limits. I will use the other one maybe because that would be another example. So f of 0 plus h minus, oh, sorry, I am supposed to use the other one. F of x minus f of 0 over x minus 0 as x goes to 0. For this now, I know what is the value of f at 0. That's given by 0. And now we have limit of x squared sine 1 over x as x goes to 0. Okay. You may say, why did you ignore this second part, and while trying to find the limit, you just use this first formula? Well, that is a very good question. And the answer is, when we studying limit of the function as x goes to 0, we never consider the value of the function at 0. We only consider the value of the function closer to 0, but values of the function around 0. It means that when x approaching to 0, it will be a number which is definitely not 0. It will be very close, approaching to 0, but never will be 0. That's why when you're trying to find the limit, I can look at this formula and say, okay, for all values of x which is not 0, the function is given by this formula, and that's what we have. Now you cancel this one with that. If it was sine of 1 over x, we know that that limit does not exist. But when it is x times sine 1 over x, this limit exists and it is equal to 0. How do you evaluate that? Well, here is where this squeeze theorem comes in. I won't do it here because we already did the one that is x squared times sine 1 over x. It is very similar to this. Well, you have to be careful when you're setting up the inequalities, because x can be positive or negative value, but that is what it will give you. The result is that, well, yes, f is differentiable at x equal to 0, and the derivative at 0 is equal to 0. This is what we have. Any question, any comments here?
Yeah, so someone just asked why we didn't use the other formula.
Well, the other formula is only for when x is equal to 0. Yes. And oh, you mean the f of x plus h?
Yes, I think he meant
Oh,
that.
I see. It will work out as well. It will work as well because specifically when a is equal to 0, actually these two guys are going to be the same thing. See, 0 plus h minus f of 0 over h as h goes to 0. Well, that is the same thing as limit of f h minus f0 over h as h goes to 0. The only difference would be instead of using x, I will be using h. Does that?
I think it's clear, yeah.
Okay, okay. So, okay, we have another example. I will leave this example for you to complete. And let me tell you, the answer for this one is that it is not differentiable at x equal to negative. It's very interesting to do it yourself. It will be a little bit, you will need a little bit of work there, but it is very interesting and you will see that this doesn't exist for that. Okay?
Maybe then we should add if it exists in the question.
Yeah, okay. Yeah, you're right. This looks like short and informative enough. That's why. Yes, but you're right. If it exists, find it. Okay. Okay, now it's time to do something for yourself. Sinan, could
I
you
did.
please? Okay, thank you.
1 minute?
1 minute is good, yes. Maybe I'll go grab some water. Well,
In the meantime, can everybody see the polls? Good. Thank you.
okay.
Yep, we're up. Actually, we had 1 minute, 1.5 minutes, so I'm
Okay, good.
ending the poll,
Okay, thank you.
sharing the results.
So when it comes to finding what, using the graph of the function, at what points a function is differentiable or not, there are a few things that you have to remember. One is that when f is differentiable at a point, it will be continuous at that point. F is continuous. So differentiability is always something stronger than continuity. How we can use this thing, so as a result of that, if f is not continuous at a point, then it is not differentiable at that point. So those are the first point we have to check. See, at 2, the limit exists, but the value of the function and the limit are not the same. So this is not continuous. At -5, the right limit, left limit are not equal, so it does not exist. So it is not continuous. If you're not careful, you won't notice that function is not defined at 0. Not defined at 0 means that not continuous at. This way, we found at least 3 points. The other fact that you should know about the differentiability based on the graph is that sharp corners. If the graph has a sharp corner at some point, it is not differentiable at that point. So if the graph of f has sharp corner or sharp return, sharp corner, like absolute value of x at 0, it is not, f is not differentiable at that point. So in this example, every single point, other than the ones that the function is not continuous, are nice, but this piece here. So this is sharp corner, and it's not differentiable. And for this function, that's it. So we found two, is this B? There is also another case that if you have vertical tangent line. Like if a function has vertical tangent line at that point, oops, then the function is not differentiable. So not differentiable at that x equal to. We don't have any of those points here, but you can check it in the previous example that I left it as an example for you. That's actually in one of those cases. Third cubic root of x is where you have a tangent line at a point, but we don't have, the function is not differentiable at that point. Let me see. Okay. So that was that example. Maybe two more things we have to go. Okay, this is one of those. Differentiability. Check the function. Find the values of a and b and c such that the function is differentiable everywhere, while here everywhere means for all x's bigger than a -1. So it will be for all a -1. Sorry, for everything bigger than 0 plus. So when you look at these functions, well, if x is bigger than 1 and if x is less than 1, the function is differentiable. These are nice functions. But checking differentiability at x equal to 1 is what we have to start. So we need to go limit of f of x minus f of 1 over x minus 1 as x goes to 1. Let me use the other formula. This formula will work as well, but let me just use the one that f of a 1 plus h minus f of 1 over h. And h goes to 0. Here, you right away notice that first of all, we have to get closer to 1 either from the left so that this will come out, or if we go to from the right, this will come out, from the left, this will come out. So definitely we need to separate this into two limits. Either h goes to 0 from the left or h goes to 0 from the right. Okay? But you notice that f at 1 is b, and we have too many constants in the numerator. To have easier thing to deal with, it's better to find other facts, use other facts, and find some of, hoping that we can find some of these constants before we go ahead. Here, I will first check continuity at x equal to 1. You may say, okay, we are not asked to check the continuity, we are asked to check the differentiability. You are right, but we know that a function is differentiable at a point, it will be continuous at that point. By checking continuity, we are just going halfway. We are not completing the task, but we are going halfway, hoping that we will find some extra work, something there that we can use it for the other formula. So here, then we have to check limit of the function as x goes to 1 from negative value of the function, and limit of the function as x goes to 1 from positive. So f at 0, and these guys must be equal. So that is what it's supposed to be, yes. F at 1, not 0, f at 1. Okay, f at 1 is given here. The formula is equal to b. As x goes to 1 from the left, this is the formula we have to use. And that will give me, actually, I have c root of 1 plus 1, which is c plus 1. And on the other hand, when x goes to 1 from the right, we have sine of ax minus 1 over x plus 1. It may seem it's a strange thing here, but you see in the denominator, I have non-zero limit. In the numerator, sine is continuous, so I have 1.
All right, so it seems like we're having technical difficulties. Hopefully he'll come in a few seconds. In the meantime, if you have any questions about the previous example, just let me know. All right, we're back.
Okay, sorry, my computer died. Is everyone here, or?
Oh, we're here.
Yeah, okay. So just give me a second, because I want to use, or how about I just go right like this and then do this one. Okay, it is still recording. That's nice. I need to share my screen. Can you hear me? Is everything all right?
We can hear, but we don't have our screen yet. At least I don't.
Okay, is this good now?
Yeah.
Okay. So we will find the right and the left. In the right, you get sine of a times 0 over 2. This is sine 0, 0 over 2. This is 0. So these three things being equal means that, first of all, b is equal to 0. And then from that, you see that c plus 1 needs to be equal to 0. So this will give me c is equal to negative 1. We are yet to get to the final result, but so far, just by looking at this thing, we found what is c, what is b. And in other words, I can rewrite the function. The function is sine of a times x minus 1 over x plus 1, as x is bigger than 1. For x equal to 1, this is 0, b is 0. And for x is less than 1, this is, c is 1, so it is, oh, c is negative 1, so this one root, negative root x plus 1. Very nice. Now, back to the differentiability. That continuity just gave us some information. We want to now use it. Limit of f of x, so what was it? F of 1 plus h minus f of 1 over h as h goes to 0. This is limit of f of 1 is 0. How about I just go one-sided for this one? Just make everything nicer. And when h is a positive number, you add a positive number to 1. It's going to be a number bigger than 1. So I can use this formula here. So for x, I put 1 plus h minus 1 over x plus 1. Sorry, why I am doing this. So for x, I'm putting 1 plus h in this formula. So this will be 1 plus h plus 1 over h. This will give me limit of, well, but this piece here, okay, let me rewrite this thing, a. 1 plus h minus 1, this is just h over. There is this h in the denominator. I can also separate this other piece, 1 over h plus 2. Now, the limit of this piece is 1 over 2. The limit of this thing, okay, these are one of the cases that you have to know what to do. Sine of ah over ah, a outside, h goes to 0. So this is times half. And this piece here is that sine, limit of sine of box over box, as box goes to 0, that's multiplied by a times 1 over 2. This should give me 1 over 2.
1 over 2a.
1 over 2a. So a over 2, yes. Try now to find the x approaching to same thing, but this time h approaching to 0 from the right. So h from the left, f of 1 plus h minus f of 1 over h. What was the number we found actually? It is a negative 1 over 2. So this is something you can do it yourself since we are out of time now. This is -1/2. And we know that differentiability means that the limit exists. That means the right limit and left limit must be equal to each other. So a/2 is equal to -1/2. From that, we should conclude that a is negative. So that middle step, that you do continuity just to get more information, is very important and it's very useful. You start from there and then go ahead and have more things. I guess that is all I have, but there's one more example here. Just I will put it for you again. When it comes to the average rate of change, you do f of endpoint minus the right endpoint minus the left endpoint over right minus a, and that is what is called average rate of change of the function on the interval a.